Hello 10th class students, as we have completed 4 chapters, now I am going to start atomic structure. So before starting the atomic structure officially of 10th class, what you have to do is you have to go through with the textbook of 9th, which includes atoms and molecules in it. So here I am giving you a few videos of basics which you have to watch before I start the expression for chapter atomic structure or structure of an atom. This is a very important chapter. Entire chemistry starts from here. So the foundation which you need for chemistry is like starting from this particular chapter. So go through with the topics of 9th first, read the textbook and watch the videos. Then like after 3 or 4 videos, I am going to start the explanation for a structure of an atom.
Structure of atom. In our daily life, we observe that many large particles could be divided into smaller particles. Can these sand particles be divided further into smaller particles? Yes, these tiny particles can further be divided into atoms. Atoms are the basic building blocks of matter that make up everyday objects. Is every atom existing in different matter the same? What makes the atom of one element different from the atom of another element? Are atoms really indivisible, or are these smaller constituents inside the atom? Come, let us seek the answers of such questions in the module Structure of Atom. After reviewing this digital content, the students will be able to explore the discovery of electron, proton and neutron and their characteristics. Describe Thomson, Rutherford and Bohr atomic models. Define and determine the atomic number and mass number of an atom. Understand the features of the quantum mechanical model of atom. Explain the nature of electromagnetic radiation and Planck's quantum theory. Understand the photoelectric effect and features of atomic spectra. State the de Broglie relation and Heisenberg uncertainty principle. Subatomic particles. Atoms are the building blocks of elements. They are the smallest part of an element that chemically reacts. The first atomic theory proposed by John Dalton in 1808 regarded atom as the ultimate indivisible particle of matter. Towards the end of the 19th century, it was proved experimentally that atoms are divisible and consist of 3 fundamental particles: electrons, protons and neutrons. Let us discuss the discovery and properties of these particles in detail. Discovery of electron. In mid-1850s, many scientists began to study electrical discharge in partially evacuated tubes known as cathode ray discharge tubes. Let's have a look at the experiment. A cathode ray discharge tube made of glass is taken with 2 electrodes. At very low pressure and high voltage, current starts flowing through a stream of particles moving in the tube from cathode to anode. These rays were called cathode rays. When perforated anode was taken, the cathode ray struck the other end of the glass tube at the fluorescent coating and a bright spot on the coating was developed. The results of this experiment are briefed as: cathode rays consist of negatively charged electrons. Cathode rays themselves are not visible, but their behavior can be observed with the help of fluorescent and phosphorescent materials. In the absence of electrical or magnetic field, the cathode rays travel in straight lines. In the presence of electrical or magnetic field, the behavior of cathode rays is similar to that shown by the electrons. The characteristics of cathode rays do not depend upon the material of the electrodes and the nature of the gas present in the cathode ray tube. Charge to mass ratio of electron. By using cathode ray tube and applying electrical and magnetic field perpendicular to each other, as well as to the path of electrons, J.J. Thomson measured the ratio of electrical charge E to the mass me of electron. When only electric field is applied, the electrons deviate from their path and hit the cathode ray tube at point A. Similarly, when only magnetic field is applied, electron strikes the cathode ray tube at point C. By carefully balancing the electrical and magnetic field strength, it is possible to bring back the electron to the path followed, as in the absence of electric or magnetic field, and they hit the screen at point B. By carrying out accurate measurements on the amount of deflections observed by the electron, on the electric field strength or magnetic field strength, Thomson was able to determine the value of E over m as minus 1.758820 times 10 raised to the power of 11 coulombs per kilogram. Where me is the mass of the electron in kilogram, E is the magnitude of the charge on the electron in coulomb. Since electrons are negatively charged, the charge on electron is minus E. Charge and mass of electron. Charge on an electron was determined by R. A. Millikan by using an oil drop experiment, and it was found to be 1.6 times 10 raised to the power minus 19 coulomb. The mass of an electron was determined by combining the results of Thomson's experiment and Millikan's oil drop experiment, and the value is 9.1094 times 10 raised to the power minus 31 kilograms. Discovery of protons and neutrons. Now let us discuss the discovery of the other two subatomic particles, proton and neutron. Proton is a positively charged particle present in the nucleus with neutral neutrons in an atom. The discovery of proton was the part of study of canal rays or positive rays. In 1886, Eugene Goldstein discovered positive rays through a gas discharge experiment. He used a gas discharge tube, also known as the Crookes tube, with a perforated cathode. When the gas is discharged at a very high electrical potential between the cathode and anode, faint luminous rays are seen, which are extending from the holes in the back of the cathode. Since these rays are moving in a direction opposite to the cathode rays, which are negatively charged, hence they are called as positive rays moving towards the cathode. Next is the discovery of neutron. James Chadwick, in an experiment, bombarded beryllium with alpha particles. In his experiment, he observed some deeply penetrating radiations coming out from beryllium. These radiations consist of material particles. The mass of these particles was nearly equal to the mass of one hydrogen atom. Since these particles were not deflected by magnetic or electric field, therefore they were named as neutrons. The fundamental properties of the subatomic particles are briefed in the given table. Atomic models. We learnt that an atom consists of subatomic particles carrying positive and negative charges. Now let us discuss the distribution of these particles in an atom. Different atomic models were proposed to explain the distribution of these charged particles in atom. These are Thomson model of atom, Rutherford's model of atom, Bohr's atomic model, and quantum mechanical model of atom. Let us study these models one by one. Thomson's model of atom. J.J. Thomson considered an atom as a uniform positively charged sphere in which electrons are embedded. An important feature of this model was that the mass of the atom was considered to be evenly spread over the atom. This model is also called as the plum pudding, raisin pudding or watermelon model. Thomson model of atom was discarded because it could not explain certain experimental results like the scattering of alpha particles by thin metal foils. Rutherford's nuclear model of atom. In Rutherford's alpha scattering experiment, a stream of high-energy alpha particles from a radioactive source was directed to a thin foil of gold metal. The thin gold foil had a circular fluorescent zinc sulfide screen around it. Whenever the alpha particles struck the screen, a tiny flash of light was produced at that point. He observed that most of the alpha particles passed through the gold foil undeflected. A small fraction of the alpha particles got deflected through small angles, and a very few alpha particles did not pass through the foil but suffered large deflections, nearly 180 degrees. From the observations drawn from the alpha scattering experiment, Rutherford found that most of the space in the atom is empty, and a positive mass is present in the atom that occupies a very small space. On the basis of above observations and conclusions, Rutherford proposed the nuclear model of atom. According to this model, an atom consists of a nucleus which is concentrated in a very small volume. The nucleus comprises of protons and neutrons. The electrons revolve around the nucleus in fixed orbits. Electrons and nucleus are held together by electrostatic forces of attraction. There were few drawbacks of this model, because of which it was not fully accepted. According to Rutherford's model of atom, electrons, which are negatively charged particles, revolve around the nucleus in fixed orbits. Thus, the electrons undergo acceleration. According to electromagnetic theory of Maxwell, a charged particle undergoing acceleration should emit electromagnetic radiation. Thus, an electron in an orbit should emit radiation. Thus, the orbit should shrink, but this does not happen. The model does not give any information about how electrons are distributed around the nucleus and what are the energies of these electrons. Atomic number and mass number. The number of protons in the nucleus of an atom determines an element's atomic number. It is also equal to the number of electrons in a neutral atom. For example, a carbon atom contains 6 protons and has an atomic number of 6. The sum of the number of protons and the number of neutrons in an atom determines its mass number. For example, a carbon atom having 6 protons and 6 neutrons have mass number of 12. The atoms of the same element having the same atomic number but different mass number are called isotopes. For example, protium, deuterium and tritium are the isotopes of hydrogen. The atoms of different elements having the same mass number but different atomic number are called isobars. For example, the given atoms of iodine and xenon are isobars. Developments leading to the Bohr's model of atom. Niels Bohr utilized the different experimental results to improve upon the model proposed by Rutherford. 2 developments played a major role in the formulation of Bohr's model of atom. These were dual character of the electromagnetic radiation, which means that radiation possesses both wave-like and particle-like properties. Experimental results regarding atomic spectra, which can be explained only by assuming quantized electronic energy levels in atoms. Wave nature of electromagnetic radiation. James Maxwell in 1870 suggested that when electrically charged particles move under acceleration, alternating electrical and magnetic fields are produced and transmitted. These fields are transmitted in the forms of waves called electromagnetic waves or electromagnetic radiations. Let us discuss some basic properties of these radiations. The oscillating electric and magnetic fields produced by oscillating charged particles are perpendicular to each other, and both are perpendicular to the direction of propagation of the wave. Electromagnetic waves do not require medium and can move in vacuum. These electromagnetic radiations are characterized by the properties, namely wavelength, frequency, velocity, and wave number. Wavelength is defined as the distance between two neighboring crests or troughs of wave. It is denoted by lambda. Frequency may be defined as the number of waves which pass through a particular point in 1 second. It is denoted by mu. Velocity is defined as the distance traveled by a wave in 1 second. In vacuum, all types of electromagnetic radiations travel with the same velocity. Its value is 3 times 10 raised to the power 8 meters per second. It is denoted by V. The frequency, wavelength and velocity of light are related by the given equation. Wave number is defined as the number of wavelengths per unit length. Particle nature of electromagnetic radiation. The first concrete explanation for the phenomenon of the black body radiation was given by Max Planck in 1900. An ideal body which emits and absorbs radiations of all frequencies is called a black body. The radiation emitted by such a body is called black body radiation. According to Planck's quantum theory, radiant energy is emitted or absorbed discontinuously in the form of small packets of energy called quanta. Each such quantum is associated with a definite amount of energy, E, which is proportional to the frequency of the radiation. That is, E is proportional to mu, or E is equal to h mu, where h is the proportionality constant, universally referred to as the Planck's constant. Its value is 6.63 times 10 raised to the power minus 34 joules second. In the case of light, the quantum of energy is called photon. The total amount of energy emitted or absorbed by a body is whole number multiple of the quantum, that is, E is equal to nh, where n can take values 1, 2, 3, 4 and so on. Photoelectric effect. Albert Einstein used the Planck's quantum theory in 1905 to explain the photoelectric effect. The phenomenon of ejection of electrons from the surface of metal when light of suitable frequency strikes it is called photoelectric effect. The ejected electrons are called photoelectrons. The number of electrons ejected is proportional to the intensity or brightness of light. For each metal, there is a characteristic minimum frequency below which the photoelectric effect is not observed. This is called the threshold frequency. If the frequency of light is less than the threshold frequency, there is no ejection of electrons, no matter how long it falls on the surface or how high its intensity is. The minimum energy required to eject electrons is called the photoelectric work function. It is denoted by W naught. W naught is equal to h mu naught, where h is the Planck's constant and mu naught is the threshold frequency. Energy of the ejected electrons can be determined by the given relation. H mu minus mu naught is equal to half MeV square, where h is the Planck's constant. V is the frequency of radiation. Mu naught is the threshold frequency. Me is the mass of the electron. V is the velocity associated with the ejected electron. Atomic spectra. When a white light is passed through a prism, it splits into a series of colored bands known as a spectrum. Spectrum is of two types, continuous spectrum and line spectrum. The spectrum which consists of all the wavelengths is called continuous spectrum. whereas the spectrum in which only specific wavelengths are present is known as a line spectrum. It has bright lines with dark spaces between them. Electromagnetic spectrum is a continuous spectrum. It consists of a range of electromagnetic radiations arranged in the order of increasing wavelengths or decreasing frequencies. It extends from radio waves to gamma rays. Atomic spectra. Spectrum is also classified as emission and absorption spectrum. Let us discuss these one by one. Emission spectrum. A substance absorbs energy and moves to a higher energy state. The atoms, molecules or ions that have absorbed radiation are said to be excited. Since the higher energy state is unstable, they return to the more stable energy state by emitting the absorbed radiations in various regions of the electromagnetic spectrum. The spectrum of radiation emitted by a substance that has absorbed energy is called an emission spectrum. Absorption spectrum is the spectrum obtained when radiation is passed through a sample of material. The sample absorbs radiation of certain wavelengths. The wavelengths which are absorbed are missing and come as dark lines. Line spectrum of hydrogen. When an electric discharge is passed through gaseous hydrogen, the H2 molecules dissociate and the energetically excited hydrogen atoms emit electronic radiation of discrete frequencies. The hydrogen spectrum consists of several series of lines named after their discoverers. These series are Lyman, Balmer, Bastian, Brackett and Pfund series. The Swedish spectroscopist Johannes Rydberg noted that all series of lines in the hydrogen spectrum could be described by the given expression. Mu bar is equal to 109677 1 over n1 square minus 1 over n2 square centimeter inverse, where n1 can take values 1, 2 and so on, and n2 is n1 plus 1, n1 plus 2 and so on. Mu bar is the wave number of the spectrum. The value 109677 centimeter inverse is called the Rydberg constant for hydrogen. Bohr's model for hydrogen atom. In 1913, Niels Bohr proposed a model of an atom based on the Planck's quantum theory of radiation. An atom consists of a small positively charged nucleus around which electrons revolve in definite circular paths called orbits. These orbits are associated with definite energies called energy levels. They are designated as K, L, M, N, etc., shells, or numbered as 1, 2, 3, 4, etc. from the nucleus. As long as the electron remains in a particular orbit, its energy remains constant. This accounts for the stability of an atom. When transition occurs between two stationary states that differ in energy, the frequency of the radiation absorbed or emitted can be calculated by the given relation. Mu is equal to delta E over H, which is E2 minus E1 over H, where mu is the frequency of radiation, H is the Planck's constant, E1 and E2 are the energies of the lower and higher energy states respectively. An electron can move only in those orbits for which its angular momentum is an integral multiple of h over 2 pi, that is MEVR is equal to n times h over 2 pi, where n can have values 1, 2, 3 and so on. Bohr's theory of hydrogen atom. The basic postulates of Bohr's theory are as follows. The stationary states for electron are numbered in terms of principal quantum number as n is equal to 1, 2, 3 and so on. For hydrogen atom, the radii of the stationary states are expressed as R0, Rn is equal to n square A naught, where the value of A naught is 52.9 picometers. So the radius of the first stationary state, called the Bohr orbit, is 52.9 picometers. Energy of stationary state is determined by the given relation. En is equal to minus Rh times 1 over n square, where Rh is called the Rydberg constant with value 2.18 times 10 raised to the power minus 18, and n can take values 1, 2, 3 and so on. For ions containing only one electron, energy gets modified and is given by En is equal to minus 2.18 times 10 raised to the power minus 18 multiplied by Z square over n square joules, where n can have values 1, 2, 3 and so on. The radius is equal by Rn is equal to n square A naught over Z equal to 52.9 n square picometer, where Z is the atomic number. Though Bohr's model of the hydrogen atom was an improvement over Rutherford's nuclear model, it still had few limitations. Bohr's model failed to account for the finer details of the hydrogen spectrum. For instance, splitting of a line in the spectrum into two closely spaced lines. Bohr's model was also unable to explain spectrum of atoms containing more than one electron. This model was unable to explain Zeeman effect, that is, splitting of spectral lines in the presence of magnetic effect. It also failed to explain Stark effect, that is, splitting of spectral lines in the presence of electric field. Bohr's model could not explain the ability of atoms to form molecules by chemical bonds. Towards quantum mechanical model of the atom. Two new concepts came to substantially modify Bohr's atomic model. These are dual behavior of matter and Heisenberg's uncertainty principle. Let us first discuss dual behavior of matter. De Broglie suggested that all material objects, including an electron, have a dual character. That is, they behave as particles as well as waves. The wavelength lambda associated with a particle of mass m moving with velocity v is given by the de Broglie equation. Lambda is equal to h over mv, which is also equal to h over p, as we know that momentum is the product of mass and velocity of a particle. Now let us discuss Heisenberg's uncertainty principle. It states that it is impossible to determine simultaneously the exact position and exact momentum or velocity of an electron. Mathematically, it is given by the equation shown, where delta x is the uncertainty in position, delta Vx is the uncertainty in velocity, and delta Px is the uncertainty in momentum. This means that if the position of electron is known, the velocity of the electron will be uncertain. On the other hand, if the velocity of electron is known, precisely the position of electron will be uncertain. Significance of uncertainty principle is that it rules out the existence of definite paths or trajectories of electrons and other similar particles. The effect of Heisenberg uncertainty principle is significant only for motion of microscopic objects and is negligible for that of macroscopic objects. Quantum mechanical model of atom. Schrödinger equation. Quantum mechanical model of atom is based on a fundamental equation which is called Schrödinger equation. For a system, such an atom or a molecule whose energy does not change with time, the Schrödinger equation is written as H psi is equal to E psi, where H is the Hamiltonian operator, E is the total energy of the system, psi represents the wave function, which is the amplitude of the electron wave. When Schrödinger equation is solved for hydrogen atom, the solution gives the possible energy levels the electron can occupy and the corresponding wave functions of the electron associated with each energy level. Psi gives us the amplitude of wave. The value of psi has no physical significance. Psi square gives us the region in which the probability of finding an electron is maximum. It is called probability density. Orbits and orbitals. Electrons cannot exist at a particular point or in a well-defined orbit or path according to the new approach of wave mechanics. This led to the concept of most probable regions in space around the nucleus. These regions are called atomic orbitals, where the probability of finding the electron is maximum. Quantum numbers. There is a set of 4 quantum numbers which specify the energy, size, shape and orientation of an orbital. A. These are principal quantum number n. B. Azimuthal quantum number L. C. Magnetic quantum number ml. D. Electron spin quantum number ms. Principal quantum number. It determines the size and to a large extent the energy of the orbital. It is denoted by n. It also identifies the shell. It can have positive integer values of 1, 2, 3 and so on. Azimuthal quantum number L is also known as orbital angular momentum or subsidiary quantum number. It defines the subshell and the three-dimensional shape of the orbital. It also determines the number of subshells or sublevels in a shell. Total number of subshells in a particular shell is equal to the value of n. L has values 0, 1, 2 up to n minus 1. Each subshell corresponding to different values of L are represented by different symbols such as 0 by S, 1 by P, 2 by D, 3 for F and so on. Magnetic quantum number. It gives information about the spatial orientation of the orbital with respect to standard set of coordinate axes. For any subshell L, 2, L plus 1 values of ml are possible. For each value of L, M, L has values from minus L to plus L including 0. Electron spin quantum number. It refers to orientation of the spin of the electron. It can have 2 values, plus half and minus half. Plus half identifies the clockwise spin and minus half identifies the anti-clockwise spin. Shapes of atomic orbitals. A function that describes the wave-like behavior of either one electron or atomic orbital is a mathematical pair of electrons in an atom. This function can be used to calculate the probability of finding any electron of an atom in any specific region around the atom's nucleus. Each orbital in an atom is characterized by a unique set of values of 3 quantum numbers n, L and m, which correspond to the electron's energy, angular momentum and an angular momentum vector component respectively. The simple names S orbital, p orbital and d orbital refer to the orbitals with angular momentum quantum number L equal to 0, 1 and 2 respectively. The s orbital is a spherically shaped region describing where an electron can be found within a certain degree of probability. All s orbitals have L equal to m equal to 0, but the value of n can vary. A node is a place where there is 0 probability of finding an electron. A radial node has a spherical surface with 0 probability. More is the number of nodes, higher is the energy of the orbitals. For p orbital, L is 1 and m is plus 1, 0 and minus 1 means there are 3 p orbitals which is symbolized as px, py and pz. Shape of p orbital is dumbbell in which the 2 lobes are on the opposite sides separated by the nodal plane. P orbitals has directional properties. The size, shape and energy of all the 3 orbitals are equal. They only differ in their orientation. For d orbital, L is 2, then the values of m are minus 2, minus 1, 0, plus 1 and plus 2. It shows that there are 5 d orbitals designated as dxy, dyz, dzx, dx square, dy square and dz square. Each d orbital is identical in shape, size and energy. The shape of d orbital is double dumbbell. It has directional properties. Energies of atomic orbitals. The relative energies of various orbitals of single electron atom depend on the value of the principal quantum number n and is independent of the value of I. This can be shown by an arrangement known as the energy level diagram. The given diagram illustrates the relative energy of various energy levels for hydrogen and hydrogen-like atoms. For a particular main energy level, the orbital having higher value of the azimuthal quantum number L has higher energy. In general, energies of orbitals belonging to the same main energy level follow order S less than P less than D less than F. Orbitals with lower value of n plus L are filled first as they have lower energy. If two orbitals have the same value of n plus L, then the orbital with lower value of n will have lower energy. Filling of orbitals in atom. The filling of electrons into the orbitals of different atoms takes place according to Aufbau principle, Pauli's exclusion principle, and the Hund's rule of maximum multiplicity. Aufbau principle. In the ground state of the atoms, the orbitals are filled in order of their increasing energies. The order in which the orbitals are filled is given as, it is based on n plus L rule. It states that the orbital with lower value of n plus L has lower energy. Pauli's exclusion principle. No two electrons in an atom can have the same set of 4 quantum numbers. Only 2 electrons may exist in the same orbital, and these electrons must have opposite spin. Hund's rule of maximum multiplicity. Pairing of electrons in the orbitals belonging to the same subshell P, D or F does not take place until each orbital belonging to that subshell has got 1 electron each, that is, it is singly occupied. Electronic configuration of atoms. The distribution of electrons in different orbitals is known as its electronic configuration. This can be represented in 2 ways: s raised to the power a, p raised to the power b, d raised to the power c, and so on notation. In the first notation, the subshell is represented by the respective letter symbol, and the number of electrons present in the subshell is depicted as the superscript like A, B, C, etc. Orbital diagram. In the second notation, each orbital of the subshell is represented by a box, and the electron is represented by an up arrow for a positive spin or a down arrow for a negative spin. Based on the various rules of filling the orbitals, the electronic configuration of some of the important elements is shown. In some cases, the actual configuration differs slightly from the expected ones. Examples are copper, atomic number 29, and chromium, atomic number 24, because of the condition of achieving extra stability by half-filled and completely filled subshell configuration. Let us summarize the main points covered in this digital content. Atoms are the building blocks of elements. They are the smallest part of an element that chemically reacts. The first atomic theory, proposed by John Dalton in 1808, regarded atom as the ultimate indivisible particle of matter. Towards the end of the 19th century, it was proved experimentally that atoms are divisible and consist of 3 fundamental particles: electrons, protons, and neutrons. Different atomic models were proposed to explain the distribution of these charged particles in atom. These are Thomson model of atom, Rutherford's model of atom, Bohr's atomic model, and quantum mechanical model of atom. Thomson proposed that atom is considered as a uniform positively charged sphere in which electrons are embedded. According to Rutherford, an atom consists of a positively charged nucleus which is concentrated in a very small volume. The nucleus comprises of protons and neutrons. The electrons revolve around the nucleus in fixed orbits. dual character of electromagnetic radiation, and experimental results regarding atomic spectra were the two developments which played a major role in the formulation of Bohr's model of atom. As light is propagated in the form of energy packets called photons, it can be treated as particles of light. On the other hand, as light also exhibits the phenomena of interference and diffraction, which indicates that light also has wave-like character. Thus, light has dual character, that is particle as well as wave character. When a white light is passed through a prism, it splits into a series of colored bands known as spectrum. It is classified as emission spectrum and absorption spectrum. Bohr postulated that electrons move around the nucleus in circular orbits. Only certain orbits can exist, and each orbit corresponds to a specific energy. The wavelength associated with a particle of mass m moving with velocity v is given by de Broglie's relation. Lambda is equal to h over mv. Heisenberg's uncertainty principle states that it is impossible to determine simultaneously the exact position and exact momentum or velocity of an electron. For a system, such as an atom or a molecule, whose energy does not change with time, the Schrödinger equation is written as h psi is equal to E psi. A set of 4 quantum numbers specify the energy, size, shape and orientation of an orbital. These are principal quantum number, azimuthal quantum number, magnetic quantum number, electron spin quantum number. According to the quantum mechanical model of the atom, the electron distribution of an atom containing a number of electrons is divided into shells. The shells, in turn, are thought to consist of one or more subshells, and subshells are assumed to be composed of one or more orbitals which the electrons occupy. The filling of electrons into the orbitals of different atoms takes place according to Aufbau principle, Pauli's exclusion principle, and the Hund's rule of maximum multiplicity.